Hello, hello, hello. Today is Thursday, May 16, 2024. And here follow the solutions to problem 201. You will see Keith Norman's video solution. Straightforward, Newtonian mechanics. This problem is all about the conservation of total energy and the conservation of angular momentum. Was it difficult? No, I don't call this a difficult problem. And I'm pleased to know that in addition to Eugen and Keith, who always have the solutions right, that there are several others who have correct solutions. And I'll show them to you here, although I cannot really pronounce their identifications. You have to read them. Verzen-Topramos. Hannah Yak 7746. Ulf Heller, you know him of course. Ulf also calculated capital V and V0 by assuming that m is the mass of Earth and r the Earth's radius. He then finds that V is 0.36 kilometers per second and that V0 is 10.8 kilometers per second. Of course, I didn't give you m and r, but it's nice that he added this, that he's pointing out basically if you knew m and r, you could actually also calculate V0 and V. Photonenbremse. Carlroach, he often has things right. Okay, if you're ready, here comes Keith Norman's solution.
This is Keith's solution to Walter Lewin's problem 201, and everything we need to know about 201 we could find in his lecture 22 of 801. We have a planet, mass m, and we launch a little mass at some velocity v0 at an angle of 30 degrees to the local vertical. So in part A we have an unbounded orbit, the mass just flies off somewhere to infinity, and in part B we're told, parts B, C and D we're told that the orbit is bounded, so it reaches some maximum and then starts to come back. Okay, so we're told the planet is non-rotating, and as usual little mass is much less than the big mass, so that is stationary. Also, by launching at 30 degrees, or in fact any angle, we are going to be introducing angular momentum, and we need to consider that at some point. And we're also told that there's no atmosphere, so energy is conserved for the whole system. We've got no frictional losses. So, part A. You should be familiar with this kind of diagram by now. At our launch condition, we have the potential energy of the mass is going to be minus gmm over r, and we need to just escape orbit. We need to travel up this potential well, as it were, and reach a zero potential energy condition out at infinity. So we need to add kinetic energy to get there. Our kinetic energy is a half mv0 squared. As I've said, our initial potential energy is minus gmm over r. Remember, it's minus. At infinity, we don't want any spare energy for a minimum velocity, so we will have used up all of that. That will be zero at our infinity, or heading to infinity, as will our gravitational energy, because we define it as zero out at infinity. So that gives us a minimum velocity for escape of this here, and that's our familiar escape velocity. And note, excuse me, note it doesn't matter what angle of launch we have. It might affect the path we take, it will affect the path that the mass takes, but it doesn't affect the minimum energy and hence the minimum velocity that we need. Okay, for part B, we have 2 points that we need to consider, and we're going to do this with conservation of angular momentum. We need to consider our angular momentum here and here. Okay, so we have at start, this is our condition, v tangential times r, and we have at our maximum orbit, maximum distance from the planet, we have mv max, and we're told that our maximum radius, maximum distance is 15r. We're told that the angle of launch is 30 degrees, so v tangential will be v0 sine 30, or v over 2, hence v0 over v, the ratio is 30. For parts C and D, well, we know that the energy at start is going to be a starting condition there, and we know by way that it's also less than 0 for a bound orbit. We know our total energy, which is conserved of course. We know our total energy at our maximum radius is going to be, just feeding in the values for V and R, this here. So that gives us C and D. But we also know that energy is conserved, so we can compare these two and do a bit of simplification. So as I say, C and D are equal, energy is equal. So if I equate that term and that term, I get this, which I simplify, and I see that V0 squared must be this expression here. Note that if I take the square root of that, I get roughly 4 over 3, which is less than root 2. So we have confirmed that yes, this velocity here is going to be less than our escape velocity, so we do have a bound orbit. So if I feed back this into one of these expressions, I can see that the total energy cannot be expressed for both C and D, because energy is conserved. I can either express the total energy as this here, or that there. And that is my solution to Walter Lewin's problem 201. Thank you.